Okay, so we have just a little bit to go in terms of what we've been talking about, which is pretty much the last part of 15. We're going to talk or finish up the example that we're doing. So last time we were right in the middle of that titration example. It was this one here, I believe. And we're doing a titration, as we talked about last time, of a weak acid and a weak acid and a strong base in this case. Again, the weak acids in the beaker, the flask, whatever it may be there that you're using. Obviously, the strong base is up there in the burette, and we're adding obviously the base to the acid. So as we talked about a lot as we were going through sort of the titration process here, really, really important to make sure that you sort of understand what titration you're doing, obviously. And we talked about that really in all these titrations, there's really kind of like four parts to each of them. So if you could really have a pretty good understanding of where you are in the titration, you oftentimes, before you sort of really start the calculation, should have a pretty good understanding of sort of what type of problem you should be doing. You also should have a very good understanding of what sort of the expected pH should be at that point. Should it be acidic? Should it be basic? Should it be neutral? And again, as we talked about, these are things you want to think about as you're going through these problems so that you're able to hopefully avoid a lot of common mistakes. The good news is a lot of the calculations that we do in these things, as we've been seeing, are really calculations that we've done before. The real trick here is to make sure that you understand when you should sort of apply that calculation or what is happening there. So if I'm not mistaken, I believe we did their A and B. So we're on C, I believe now, which is in this titration here. We're trying to figure out what we have in terms of the pH at the equivalence point. So we're doing 100 milliliters of nitrous acid there. So I'm going to go find a place to scribble here. A, B, and C. I guess that comes next. All right. So C, and again here, we're starting with 100 milliliters of our 0.1 molar nitrous acid. We're adding 0.1 molar sodium hydroxide, I believe, in this case. And they also gave us a Ka value, which was 4.5 to the minus 4. So here, as it mentioned, we want to figure out what is the pH at the equivalence point. So again, this is a problem where, as we also spoke about yesterday as well, they really didn't give us a volume to get there. So again, there's a couple ways you could kind of go about figuring out, what is the volume needed to reach the equivalence point. We definitely know we're going to have our reaction, which is our HNO2 plus our sodium hydroxide, going to get us some NaNO2 and some water here. We obviously know our initial moles here of our HNO2 is 0.1 times 0.1, which is 0.01 moles. And obviously we do want to do this in moles since we are adding volume. Again, a couple of pieces of information, right? So since we do know we're at the equivalence point, really, we do know that this guy should be the same number. We also know that we can, because this is a one-to-one relationship, if we want to kind of quickly figure out the volume to reach that equivalence point, we could solve for V2 here, where obviously M1 is our acid, V1 is the amount of our acid, M2 is the molarity of our base, and V2 there is the volume. So when we solve for V2, we actually do need 100 milliliters to reach the equivalence point. By the way, if it is a one-to-one relationship and these guys have the exact same molarity, you need the exact same amount to reach the equivalence points. That's also another way you could do it. So this tells us that 100 milliliters is needed to reach the equivalence point. And if you did that before you figured this out, you then could use molarity, obviously, and figure out that the moles would be the liters times our molarity from above gets us our number that we got there. So as I think we kind of talked about the other day, there's a kind of multitude of ways that you could probably figure out, where you're at in terms of moles for sure, because these guys should be equal, but you could also figure out the volume needed to reach the equivalence point. Any questions on that there? And I think I also went over it the other day. When we do this sort of calculation here, again, it is really just will work for a one-to-one relationship, but it really is doing the stoichiometry, right? It's kind of the multiple relationship and everything that's happening. It works out because it's a one-to-one relationship. You don't have to worry about it. That's going to be 0. Here, we can't really screw it up since it is the same number on both sides. So it's got to be that number as our change. That means, as we would expect in this case, all the acid we started with is gone. All of the strong base we added is gone. And we are left with this many moles of this guy here. Also, why it's important, again, to figure out what the volume is to reach the equivalence point, because now you know your total volume is going to be the 100 milliliters we started with of the acid, and obviously the 100 milliliters of the base we need to add, giving us 200 milliliters as total volume. And that is obviously critical here to getting the correct molarity at this point by dividing by 0.2. So 0.01 divided by 0.2 gets us 0.05 molar. Any questions on that ice table, where any numbers came from or anything like that? Okay, so now, like we talked about before, again, if you're maybe still unclear on where to go next, again, your ice table can be very helpful for you. We see that obviously all we got pretty much left is this sodium nitrite. That is a salt. That is a salt that will break apart into a sodium ion and a nitrite ion. And from our talk about salts over the chapters here, like normal, this guy is a neutral salt because obviously it came from like sodium hydroxide. But this guy here, which obviously came from this weak acid, is going to go through hydrolysis. And this is what we would expect to happen here at this point. We would expect a hydrolysis reaction to occur between this part of the salts and water. And again, because it came from a weak acid, it's going to act as a base, not to mention the fact it doesn't have a hydrogen, so it can't give it. So it's got to receive it here. And when it does here, we will end up with HNO2 where it came from. And we will end up with hydroxide being produced. And as we predicted as well, or should be able to predict even before we started the calculation, we should expect this guy to be basic because of the salt that's being generated. Any questions on that? At this point, it's an ice table, so we're going to use our equilibrium value here as our initial value. So we're going to carry it down because obviously at this point in the titration, that is the concentration of our nitrite. We could do it in molarity at this point. Everything has been added. And we would do this table with x's. Getting a 0.05 minus x, x, and x. This is going to go into our K expression, which is our products over our reactants. And the other important thing that we talked about as well is that is OH minus, which means this is a KB, not a Ka value. So again, just like we had with regular sort of salt problems, we do need to sort of convert our K value to the correct one here, and using the Ka that was given to us, and that Kw equals Ka Kb. Our Kb in this case would be Kw divided by the Ka. So that is 1 times 10 to the minus 14 divided by our 4.5 times 10 to the minus 4. And that's going to get us here. Looks like 2.2 to the minus 11, we'll call it. And that is, again, the value that we want to make sure that we use here. Putting our x values in will give us x squared divided by 0.05 minus x, equaling our 2.2 times 10 to the minus 11. We might as well go for the assumption since that is to the minus 11, so that's fairly small. We're going to assume that x is equal to 0. That will get us x squared 0.05 is equal to our 2.2 times 10 to the minus 11. And at this point, that will then get us, do a little square root action there. That's going to get us something like x is equal to 1.05 times 10 to the minus 6. We do want to check it, so we're going to divide that by 0.05 times it by 100. And I think we should be fairly good here. And we are, it's not even 1%. So we are good on that number. So the check is good. That means that this x value, as we can see from our ICE table, obviously here, is equal to our OH minus. So x equals the concentration of our OH minus. Also important to remember that means that we cannot get the pH right now. We can start with our POH first, minus the log of 1.05 times 10 to the minus 6. And looking like we end up with a 5.98 as our POH. And again here, if for some reason you thought that that was the pH, it again should not make sense to you because again should be basic. So in case you got mixed up or something and you thought that happened to have been the pH value, these are the things we want to think about to make sure we don't kind of screw it up there. We're going to take 14 minus that. So I try to squeeze it in here at the end, looking like we're going to end up with 8.02 as our pH here at the equivalence point, which obviously does make sense based on the fact that we are producing hydroxide and we would expect a basic pH at this point. Question on any of those steps along the way. Hopefully you could kind of see that, you know, it is really the same sort of calculations we've done before. The only difference is here, you know, you got to make sure you kind of apply these things in the right sort of way. Any questions on any of those steps? Okay, so that was then C. So let's go back and take a look at what D was asking for. How much base there? 105 milliliters of base for D. So let's take a look at D and see what happens here. And okay, so D, we are adding 105 milliliters of our 0.1 molar sodium hydroxide to our 100 milliliters of our 0.1 molar nitrous acid. So obviously, just like the other steps there, pretty much we're going to have our same reaction occurring. We're going to get the moles of everybody here since we have it all given to us. So really starting with the same moles of our acid there, which is 0.01 moles. 0.105 times 0.1, 0.105 on this guy and this. Now, clearly in this problem here, we're kind of continuing on from the previous step. So again, you should be able to recognize that you are definitely past the equivalence point. But if this was sort of a standalone problem, again, as we talked about, you can use your ice table there to figure it out. And again, just comparing the moles of the acid to the base, in this case, our acid moles is less than the base moles. And that tells us that we are definitely past the equivalence point in this type of titration. And again, those are good things to keep in mind. That means that obviously we have that change that occurs that really at this point, the acid becomes kind of the limiting reagent. And the change would be that guy, the smaller number. Again, keep in mind just basic logic of you cannot have a negative concentration or moles and stuff like that. So go with the smallest number. This is going to be 0. That's going to be not 0. So that's going to be, let's see here, 0.0105 minus 0.01. That's a lot of zeros there. That's going to be 0.00005 moles and 0.01 moles of this guy. At this point, in terms of our total volume, we started with 100 milliliters of acid. We added 105 milliliters of the base. That is 205 milliliters. And again, that is what we would use to 205, not 250. That's what we would use to convert it back to molarity here. And so I'll try that number again, 0.205 liters and 0.205 liters. And if we do that, we will end up with 0.00244 molar for that guy and 0.0488 molar for that guy. And again, if you're not sure what's happening here, even though you kind of should have a pretty good understanding of what's happening at this point, we do have sodium nitrite, we do have sodium hydroxide. And again, as we've talked about before, they are not related to each other. So again, just because you got two numbers doesn't make it a buffer, even though you might want it to be. So what we got going on in this case is, again, sodium nitrite, which is definitely a base like we saw in the previous step, definitely going to generate some hydroxide. But we do, again, have the presence of this strong base here. And again, with the presence of that strong base, it is probably going to be the major contributor here. So as we've talked about before, at this point in these titrations, we pretty much ignore the contribution happening over here. And we look at really just the strong base, which means because that's a strong base, that is going to equal our OH minus concentration, which means we could go right into our POH. And I suppose you get some numbers, perhaps. 1.61. Again, if you got confused somewhere and thought that was the pH, if you understand what's going on, that again should definitely not make sense to you because you're pretty much past the equivalence point, which means you're pretty much just dumping that base in there all day, every day, 7 days a week on that thing. So you should have a lot of OH minus floating around in there. So that's going to be 14 minus or 1.61.
Professor?
Yeah.
It's 0.0024, not 0.
Yeah.
Is it? Which one?
2 zeros after the decimal point.
Is it really?
Yeah.
Thank you very much.
You're welcome.
Hate those extra zeros. Let's try that again. Thanks, guys. So it is minus the log of 0.00244, actually 2.61. Still shouldn't make sense to you, I suppose, at 2.61. Thank you. So we'll do that. Not too much damage. Thank you. Let's get 1139. I'll do the classic. I was just making sure everybody was paying attention. Yes, I did screw up very much. All right, 11.39, which again would obviously make sense here as we are definitely, like I said before, pretty much at this point just dumping in sodium hydroxide, which is generating a lot of free OH minus. And this is the point, really, if you think about this sort of titration curves, once we hit that equivalence point, as we talked about, you pretty much have just used up all that acid. So by just dumping that sodium hydroxide, a lot of free OH minus really quickly, which is why, again, we kind of see that big jump that usually occurs till kind of that hydroxide level sort of levels out on the top part of the curve. Any questions on any of that there? Don't forget zeros. That would be good. Any questions on titrations, how to do these calculations? So obviously, as we talked about, you do need to be able to do these type of problems for the 3 types of titrations that we talked about, which is, again, a strong acid, strong base, a weak acid, strong base, and a strong acid, weak base type titrations, and be able to obviously figure out the pH anywhere along those curves. And again, you should hopefully have a pretty good understanding of what's going on at any point along the way. Any questions on titrations in general?
Yeah, could you explain again why you ignored the NaNO2 in the problem?
At this point in the titration over here?
Yeah.
Yeah, so basically, really, if you just kind of think about what's going on at this point in the titration, if you kind of zoom into like the beaker or whatever is there, you definitely do have that NaNO2 there, which is basically going to make Na plus and NO2 minus guys floating around. And you're basically, majority of what you're doing at this point is you're dumping the sodium hydroxide in there, which is also going to make some more sodium ions. But it's going to essentially just make a lot of hydroxide pretty quickly, because essentially what's going to happen when you dump the sodium hydroxide in, it pretty much just needs to go for a swim to generate those hydroxides. When we have that sodium nitrite that was made, it needs to then go find water and do a little reaction, right, to generate that hydroxide. So at this point in titration, you have both of those things happening. But it's kind of like, this is just going to be your major supplier of hydroxide at that point, because it doesn't really have to do anything other than pretty much go in for a swim into that beaker. And it's just going to generate that hydroxide very, very quickly. And that's why it's going to be, out of the 2, really sort of the major contributor at that point in terms of hydroxide that's going in. If you think about sort of even, not exactly the right idea here, but if you think about sort of what we had here in that part where the sodium nitrite was making hydroxide, it's like times 10 to the minus 6, which is a very, very sort of small amount, if you will, in terms of hydroxide being made, as it compared to this guy where I won't say he's almost full strength, but he's going to be a lot greater strength of hydroxide going into that solution. So although this is happening, it takes a little bit more work to generate it, and not as much is going to be generated as when the sodium hydroxide basically goes in, because basically all it has to do is go in, and it, boom, you have kind of like instant hydroxide at that point once it goes in. Other questions on that? So that's why, again, we ignore it at that point, because again, we think about sort of which one's going to be the major contributor, and it's going to be that sodium hydroxide. It's kind of like when we talked about the polyprotic acids, and when that first H plus comes off, that's pretty much the majority of the H plus that comes off. Although in the second step or the third step, when the H plus comes off, it comes off, but it only produces like 0.000 down the road, a very small amount of it. And the same idea here, even though they're both really producing hydroxide, that salt has nowhere near the ability to produce as much hydroxide as that strong base. Other questions on that?
Okay, thank you.
You're welcome. Other questions on titrations or parts of the calculations or anything like that? Okay. So that obviously wraps up, I believe, chapter 15. So we are then going to roll into chapter 16 now, since I believe we talked about indicators before we did this problem. So we should be good on that. So let me get that going here. I think I might even have it here. Let's go that way. Okay, so we're going to talk about chapter 16. We're going to talk about KSP, which is basically the solubility product So as we'll talk about here, we're going to talk about everything in chapter 16 except for maybe I think the very last section, and then we'll come back to the last section a little bit later on in the semester. So we're talking about KSP. KSP is really an equilibrium constant for kind of things that are insoluble. So as odd as it sounds, KSP is that equilibrium constant for things that are considered based on solubility rules to be insoluble. SP stands for solubility product. And although when we think about sort of solubility rules, we sometimes think about them as being 100% always the case. And it's really not the case. As we will see in this chapter, there is a lot of things that can affect the solubility. There's a lot of things that can affect whether or not perhaps you see a solid or don't see a solid. So even though solubility rules says, hey, when you put a silver guy together with a chloride, you're going to get a solid, there are a lot of factors involved as to whether or not you will actually see that solid form. Some things that affect solubility that we'll talk about in this sort of chapter, things like concentration is a very important sort of aspect of, whether or not you'll sort of see that solid form. Also, things like pH, things like common ion play an important role in, again, whether or not, even though solubility rules tell us, hey, I should see a solid, you might not see a solid in certain cases. Now, other things that sometimes are hard for people to sort of grasp is when people think about things based on solubility rules as being insoluble, we always think, oh, it's a solid. But anything, even things that are technically insoluble, have some degree of solubility. So even though things that are solid, they can actually break apart into ions. And this is really the basis here of KSP. And these are how these KSP reactions are pretty much written. Solid guys goes to ions on the product side. So this is typically how we see these reactions written. And because KSP really is just an equilibrium constant, we would do our products over our reactants. And in this case, it will just be the products in most of the cases here, because solid is always there on the reactant side. So there's really nothing on the bottom when we do KSP. So this is sort of the general setup here for KSP. Type 1s, it is, again, really just an equilibrium sort of situation. It just happens to be for things that are insoluble. And if we look again here at something like silver chloride, and again, this is typically how it would be set up: solid on the left-hand side, aqueous ions on the right, which means basically it is just the products involved here when we do KSP. And it would be KSP here would be silver ion times the chloride ion. We would do the same thing as we've done with any other equilibrium type of expression. If we do have some coefficients, we do take those into account. So when we're dealing with KSP, it is very important to understand how these guys break apart into their ions. Do you get 1 to 1, 1 to 2, 1 to 3, 3 to 2, whatever it may be, because we do, again, just like a normal equilibrium expression, include those guys as the exponents here as well. So as we can see here, magnesium times F minus squared because of the coefficient, silver squared because of the coefficient, times the CO2, and calcium cubed times phosphate squared because of the coefficients there. Again, in each of these cases, which is pretty much how these guys are written, solids on the left-hand side. Also, a fairly safe hint is if you have a KSP value for something, it's probably starting as a solid. So again, even though based on solubility rules, we may think of these things as always being solids, there is, again, a degree of solubility that occurs even if things are technically insoluble. Any questions on that? So how do we know if, Would we expect to precipitate the form? Would we not expect to precipitate the form? We could actually use something that we've seen earlier on when we talked about equilibrium, and that's our good friend Q. So we could use Q like we've done before. And we could compare Q to the KSP value. A reminder that Q is the reaction quotient, and it is calculated the same as K, product over reactants, which means probably in dealing with KSP, it probably will be just like KSP products. And we could compare Q to KSP. And again, if you think about sort of how these reactions are written to aqueous ions, it is opposite of where this guy points. So if you put all the Q's on the left there, Q is less than the KSP. So opposite would mean it's going in that direction. That direction is aqueous, which means we would expect no precipitate to form. It is an unsaturated solution in that case. As you may remember what an unsaturated solution is, an unsaturated solution is a solution that if you go and dissolve more solute in it, it will continue to dissolve. It will continue to dissolve until you hit a saturated solution, and that is when Q would equal the KSP. A saturated solution is pretty much a solution where you've hit the maximum amount of solute that will dissolve at that temperature. And that means if you're at a saturated solution and you dump more solid in there, for example, it's not going to dissolve. So it's just going to start piling up there on the bottom. So that's sort of like the tipping point. And very quickly, as soon as you go past that sort of situation and Q is greater than the KSP, again, going opposite of where that's pointing, going the opposite way, that takes us to solids. And we would expect a precipitate to form in that case. And we would have what is referred to as a supersaturated solution. A supersaturated solution is basically a solution where you have way too much solute dissolved in the solvent, very unstable, and pretty much what it wants to do is kick all that solute out and make a solid form. So we could use Q, either it's given to us or we could calculate it and compare it to the given KSP value, and that will allow us to determine whether or not we would predict if we mix these two things together, should we actually see a solid form. Any questions on that there? Here's a value. You have a similar table, I think, in your book there of some KSP values for a bunch of things here. So a lot of these guys, again, if you sort of think about solubility rules, for example, right about here, that's our like group 1 there in qualitative analysis, right? Our lead 2 chloride or silver chloride or mercury 1 chloride, again, insoluble guys with KSP values. Here's our carbonates and our iodides, our bromides and our fluorides. One thing that you will notice if you kind of peruse this table, which, you know, I don't think you could probably see too much of the actual numbers here, but when you look at a KSP table, KSP values are relatively small values. So what does that really mean when we think about sort of the reaction that's occurring where we have solid on the reactant side, aqueous ions on the product side? If for the most part that the KSP values are small KSP value means that when we reach equilibrium, we mainly have reactants, which means in this situation, when we reach equilibrium, we mainly have solids, which is why we think about these things as being typically insoluble and solids most of the time. Again, it does have some degree of solubility, but for the most part, it's going to hang out over there on the sort of solid side and sort of stay together. And those small values of KSP basically sort of justify that sort of assumption that we make. So there's a couple of different sort of problems that occur here when we deal with KSP type of situations. And there's a couple of different sort of terminologies that are used for solubility. So first off, sometimes we talk about solubility in the sense of what is referred to as molar solubility. And molar solubility, I don't know if that's a fancy word for it, but it's basically the molarity there is what we're talking about. So if we talk about sort of the molar solubility of something, it's basically how many moles of that substance can dissolve in 1 liter of a saturated solution. While if we talk about just regular basic just solubility, a lot of times we're talking about a more useful sort of relationship, which is how many grams can we dissolve in a liter of solution. And there's really sort of 2 sort of approaches to these type of problems that we come across. One approach technically requires like an ice table to be done. The other approach, you could do an ice table, but you don't necessarily have to. Sort of optional, if you will, I guess. And the first approach or type of problem is they give you the solubility of the compound. Either they give you the molar solubility, they give you the regular solubility, they give you the solubility in some weird units, but they give you the solubility of this compound. From that point, you want to then convert it to the molar solubility. So if it's grams per liter, remember, if we want to go say grams per liter to moles per liter, we're really doing that conversion, grams to moles. And the way we go from grams to moles is to use the molar mass of the substance, right, in grams per mole. And that's what we use as a conversion factor. So sometimes along the way here, you need to use the molar mass of a substance to kind of do that conversion to get it from one to the next. So keep that in mind. We then can figure out the concentrations of the ions. So remember, we talked a number of times, I think at this point, that if you have an ionic compound and it breaks apart into a positive ion and a negative ion, you could do like the mole to mole relationship there. And if you know the molarity of this guy, you should be able to figure out the molarity of each of the ions. Once you do that, you have enough information basically to put it into your KSP expression and get an actual value. So that's one approach where truly you don't really need to use an ice table if you have that sort of situation occurring, but you could use an ice table and it might be helpful for you, if you wanted to. So you could use it or you might not have to. Now, there's another type of problem where it's more of a for sure you need to use an ice table. I'll put a question mark on that one. And this is a situation where the only piece of information they give you is, hey, this is the KSP for this substance. What is the solubility? And that's it. Give you no concentrations, nothing else. They just simply say, what is the solubility of silver chloride in water, for example. So in that situation, you do have to do an ice table. We would do an ice table a little bit kind of similar to what we've done before, slightly different, and we'll talk about it in just a second. That would allow you to obviously figure out what the X value is or S value and get the concentration of those ions, get the molar solubility, and then into maybe grams per liter. So one requires, again, an ice table. One really doesn't require an ice table, but you could use it. All right, so why don't we take a look at one here together and sort of see some of the subtle changes that are here that occur with these guys. So in this particular case, they tell us the solubility of silver phosphate at 25 degrees Celsius is 1.6 times 10 to the minus 5 moles per liter, or molarity, basically. We want to know what is the KSP in this particular case. So in this particular case, you don't necessarily have to do an ice table, but I'm going to show you what the ice table will look like so you have an understanding of when you do need to use an ice table for sure, sort of how to do it. So let's just talk about what approach we need to do. Well, the first thing we need to do is, since we know we're looking for a KSP for this guy, we know this guy's going to be solid. We also know it's going to break apart into some ions here. and we should get 3 silver ions when silver phosphate breaks apart, and we should get 1 phosphate ion when it breaks apart. Okay. All right, so again, if we were going to do an ice table here, we would approach this like normal. First thing that's a little bit different when we're doing sort of KSP type situations is we have solid here, which means typically we really don't put numbers on this side. So there's really no numbers that go on the left-hand side, which is a little bit different than a regular ice table that we've done before. We actually start this kind of the same way. This would be 0. This would be 0 as well. And we would then go to the change part. So the change part here, we would use a letter. Again, we're not going to worry about over here because this is a solid. So we would do the plus on this side. Now, something slightly different than is normally done, you usually use the letter X for the change part. And, you technically can use X for the change part if you like. But a lot of times people will actually use the letter S here in these tables. And the letter S actually stands for the molar solubility. So when you solve for S in these type of tables, you're solving for the molar solubility. And it's very common that people will do that. Truth be told, you could use any letter you like, but a lot of people will use S. So I'll use it here. And we do the same thing. This would be plus 3S, again, just like we do with the X's. Because the coefficient there is 3, we would go plus 3x. This would be plus s. At this point, we would carry it down like we've done before. Then we would end up with 3s and s at this point. First off, any questions on that? So the ice table looks similar to what we've done before, a little bit different again, because you pretty much have solids on your reactant side. You pretty much don't have any numbers happening there. The other difference is, again, we use S instead of X. And again, that S stands for the molar solubility. Any questions on what an ice table would sort of look like for this? And if this problem was different, where they actually gave us the KSP, we would do the problem like we would normally do at this point, which is we would write our KSP expression, remembering that we do need to cube it because of the coefficient. And this would be phosphate. And if it was a problem where they gave us this number, we would obviously do what we do with normalized tables, which is put these guys in and solve for S, and that would give us the molar solubility. But obviously in this problem, they did not give us this, so we can't really do that. So basically what we would do is, again, we would put these things in like 3S cubed, and this would be S. They didn't really give us a KSP, but they did give us this number, which is 1.6 times 10 to the minus 5 moles per liter. That is molarity. That is the molar solubility. So that actually is the S value in this case. So what we could do is just simply go into here, 3 times 1.6 times 10 to the minus 5 molar. And we want to make sure we cube it, and we're going to times it by 1.65, 1.6 times 10 to the minus 5 as well. Since this is a K, we don't really need the units there. And if we do that, that will give us 3 times 1.6 to the minus 5. And again, we want to make sure that we do cube it. And we're going to times it by 1.6 to the minus 5. And that gives us 1.8 times 10 to the minus 18 as our KSP value. Question on that step there, or that process. Okay, so in this particular problem, a couple of things. You don't necessarily have to do an ice table like I did here, but it can be very helpful for people because there's a lot of places where people think twice about doing things. Like here, like they go, well, I did the 3 here. Do I need to still do the cubing here? are what is that relationship in terms of how this guy breaks apart. So sometimes the ice table can kind of help you not miss any of those things. What I was saying earlier was that if you really understand concentrations and relationships, that you could just look at this thing like we did here and go, the concentration of the whole thing that was given to us is 1.6 times 10 to the minus 5. That's basically 3 times that number, like we talked about, how those ions relate. That gives us our 0.000048 molar. This is a 1-to-1 relationship between this guy, which means the concentration of this guy is this. You then could go right into the KSP expression and take your silver and cube it and times it by this. And obviously you would get the same answer. So if you understand sort of relationships of the molarity to the ions, you really could go kind of right into the KSP expression and basically solve for it. Or you could do an ice table, which is basically walking you through this process, right? It's going, hey, you need to take that concentration times it by 3. This guy is just the concentration. And obviously, you're just putting those things in here. So they're really the same thing. But in this particular sort of problem, you actually don't necessarily have to do an ice table, but it can be very helpful so you don't miss things like, oh, I need to multiply it by 3 and also cube it. And that's a very common thing that people sort of screw up on. They're like, I did one, oh, I didn't do the other, or I did one and not the other, or I multiplied by 3, didn't cube it, I cubed it, didn't multiply it by 3. So that's a very common sort of error. So sometimes helpful to do the ice table so you can kind of visually see what's going on. But again, if you're confident in what you're doing, like I said, you could kind of just kind of go from here to here and get the answer. Any questions on that there? Okay. So again, in this situation where you're trying to find the KSP, don't necessarily have to do the ice table, but again, may be helpful. So why don't you try one here and see what you come up with. What is the solubility of silver chloride? Let me give you the KSP to use. Why don't you use the KSP is 1.6 times 10 to minus 10 we'll use. And you might need some molar mass. So silver, what is that? That is like 107.9, I think. And chlorine is 3545 grams per mole. All right, so take a few minutes here, see what you come up with. We're looking for what is the solubility of silver chloride in water in units of grams per liter. The only piece of information given to you was the KSP when I gave it to you. So this is definitely a situation in these sort of KSP problems where you really do probably need to do an ice table. And again, the ice table is going to be set up just like we kind of did on the previous one there. We're going to have our solid guide there on the left. So our silver chloride, when it breaks apart, will produce a little bit of some silver ions, produce a little bit of chloride ions floating around. And our KSP expression in this case would be our products, which is the silver ion times our chloride. Again, no reactants here as it is a solid on that side. And that would equal 1.6 times 10 to the minus 10. Initially here, we're going to assume 0 and 0 of each of those ions. Again, we're not going to play with anything really on this side since it's a solid. Always good idea not to put things there so you don't try to use them along the way. I'm going to use, again, my S here, which is standing for my molar solubility. And again, it works just like we've used X's before. So this would be like plus X or plus S and plus S. Again, each of the coefficients here are 1. That means when we reach that equilibrium, we're going to drop those S's down. Any questions on that so far? Now, different than the previous problem, because we are given the KSP value, just like we do with regular sort of equilibrium problems, we're going to take these values and put them into our expression here. That means that we would technically get the KSP is our silver times our chloride, which basically is S squared when we put that in there, is equal to 1.6 times 10 to the minus 10. We're going to do a little square root of both sides there, right? And that's going to get us an S value of about 1.3 to the minus, looks like 5, I think. Any questions on that so far? So what does that really mean? So that S again is the molar solubility, which is basically just a fancy way of saying molarity is what that is, right? So what that tells us is the concentration of the silver ion, which equals S, equals 1.3 times 10 to the minus 5 molar. The concentration of the chloride ion, which equals S, is 1.3 times 10 to the minus 5 molar. And it asks us what is the solubility of silver chloride in grams per liter. So that would mean that the solubility of silver chloride in moles per liter would be this. And at this point, what we'd want to do is convert it into grams per liter. So we would need the molar mass, hence these two numbers here. And if we just add those guys together, 107.9 plus a 35.45, looking like 143.35 grams per mole is the molar mass of silver chloride. The grams would go on top so that we end up with grams per liter. Moles will cancel, again, leaving us, like I said, grams per liter. And that tells us that we end up with basically 0.0019 grams per liter, or 1.9 times 10 to the minus 3 grams per liter of silver chloride is the solubility of it. Any questions on that calculation there? So let's talk about a couple things here. First off, I know that we saw that the silver ion concentration was 1.3 times 10 to the minus 5. So was the chloride concentration. So sometimes people wonder, why does that mean that the silver chloride concentration is the same? And it is really about stoichiometry, right? It's basically a 1-to-1 relationship heading back. Same thing here, right? Heading back. So it comes out the same. Even if it was not a 1-to-1 relationship, say you had a 2S or something down here, which you didn't, obviously, it works out the same, that it's always S. So when you solve for S, it will really be the molar solubility of the whole thing, even if it doesn't break apart into sort of a 1-to-1 relationship. That's because, again, if this was like 2S, this would be a 2, then you would do a 2-to-1 relationship, which means there goes the 2. It ends up being S again. So one thing on these sort of problems, again, if you solve for the S, that typically is the molar solubility of the whole thing. And then obviously you could always get it back there to what you need by using the molar mass. Any questions on that? The other thing is, does this sort of make sense based on what we know about silver chloride, which is it's pretty insoluble? Well, this pretty much means that you could dissolve 0.0019 grams, which is not very much of silver chloride, in 1,000 milliliters of water. So obviously that's a very, very small amount of silver chloride that would dissolve in water under normal conditions. And obviously that's why when we think of silver chloride, we think of it as being insoluble, because you could really only get a very, very small amount of it to actually dissolve in 1,000 milliliters of water. Any questions on that particular one there? All right, then why don't you try another one here? Calculate the concentration of aluminum in this solution that has a KSP of 2 times 10 to the minus 32 at 25 degrees. So take a couple minutes, see what you come up with. KSP, so definitely we know this guy is going to be a solid here. It's also going to break apart into some ions, so we should get aluminum. And we should actually get 3 hydroxides in this particular case. We're given the KSP in this case, which the KSP expression would then be our aluminum times our hydroxide. Again, we do need to cube it because of the 3 that's there. And that would equal our 2 times 10 to the minus 32. So again, we are just given our KSP, so we need to do an ice table. So 0, 0, change again, plus S plus 3S. Again, don't forget the 3 there. Need it because of the coefficient. And we will end up with S and 3S in this particular case. That is then going to go into our KSP expression. And that would get us S times 3S cubed is equal to 2 times 10 to the minus 32. That is going to get us 27 S to the 4th. Very common. People forget to actually cube the 3. So 3 times 3 is 9, times 3 is 27. So don't forget to actually cube not only the S, but also the number. Again, a very common mistake people make. So at this point, we're going to solve for S. We're going to divide by 27, it looks like. So 2 to the minus 32 divided by 27. That is going to get us a 7.4, yeah, 47 times 10 to the minus 34. We want to take the 4th root there of that. And if you're not sure how to do that on your calculator, if you don't have that button, there's a couple of ways you could do it, but one way you could do it, and by the way, we end up with something like S is equal to 5 times 10 to the minus 9. To do this part here, you could take the 10 and sort of the caret and do 1 divided by 4. Basically, I'm not right, the caret, just the caret, 1 divided by 4, your number to the caret, 1 divided by 4 will do the 4th root. 1 divided by 2 would do the square root. 1 divided by 3 would do the cubed root and all that kind of stuff. So you take your number and then use like your caret button to kind of do that. And that's one way. Or you may have a dedicated button, which is like that. You can do that as well. So that is our S, which as we can see is the molar solubility. And that means that our aluminum concentration equals S, which would equal 5 times 10 to the minus 9 molar. It didn't ask for it, but we could also find hydroxide's concentration, which is 3 times S. So we would take 3 times our 5 times 10 to the minus 9. And we end up with 1.6. Oops, come here. Maybe. 1.6 times 10 to the minus 8 molar for our hydroxide, which, by the way, since it is hydroxide, we could actually even calculate the pOH from that if we wanted to, and we could get to the pH if we were interested in this. pH of this solution would be as well. Any questions on that? Any questions so far in KSP or anything like that there? Okay, we'll wrap up the lecture here there. At this point, I think next Wednesday, we'll take a quiz on chapter 15. So buffers, titrations, that stuff will be next Wednesday. We'll do it like we did last time. We'll just do it at the start of lab, and then afterwards we'll do the lab and stuff. Any questions on that?
Professor, did you just calculate the OH to show us? Because it
I'm
doesn't.
sorry? Yeah, it didn't ask for it, so I just calculated to show it to you. And again, in a problem like this, because it do have a hydroxide, you could also get things like the pH and POH from it as well. But in this problem, it just asked for the aluminum.
Okay.
Other questions?
Well, the quiz is not this Wednesday, but the following Wednesday.
A week from today. Today's Wednesday, right? Yeah, so a week from
No,
today.
today's
Yeah.
today's Wednesday.
Yeah, so
Oh,
a
never
week
mind. I thought today was Monday. Sorry.
I hope not. Otherwise, we're going backwards, and that's not good at all. So, yeah, no. So today's Wednesday, so a week from today. So, what is today? Like the third? So, like the 10th. The 10th, and again, like I said, we'll do it like we did last time. We'll have lecture. We'll then go meet at a meeting to take the quiz, and then we'll take a little break and go back and do the lab that day as well. Speaking of labs, today will be big titration day. We're going to do both titrations experiments today, so that should be. What is that, 8 and 9, I think, and since they're kind of very similar to each other, so we'll talk about the experiments and we'll watch both videos, and we'll knock out both of those experiments probably today, and that should hopefully put us back on track as well.